Okay, welcome back to the next part of the lesson on integer division with remainder, what I'm calling the division theorem, which is on the board already. And we have already talked about, in the last lesson, we did the strong induction proof of the existence half of this statement. But at that point, we had not yet addressed the uniqueness. And that's vital, not just that Q and R exist, the quotient and the remainder as shown here, but there's only one pair that works for a given A and B. Okay? That's what uniqueness is saying. And so let's take a look at that. And we actually haven't really done uniqueness proofs yet. We talked about what uniqueness means, and on a homework you had a proof template for how to prove uniqueness. This one's even a little harder, unfortunately, because there's actually two things. There's the Q and the R. So we have to worry. So what does that actually mean in detail? Let's take a look. So we'll fix A and B at the beginning. We don't need induction for this. But we will fix the A and the B. Of course, they're integers. And let's see. And the way you set up uniqueness proof is you say, well, what if you actually had two things that worked? In this case, a QR and then another QR, both of which satisfy these things for A and B. Well, then you'd want to show that the two Q's were equal and the two R's were equal. Okay, so let's do that. Let's in addition to the A and the B, let's fix Q and R, and I'll call them Q2 and R2 integers. And for uniqueness, unlike existence, you get to assume going in that the things you're looking at work. That's not really the issue. Assume they both work, they both satisfy this boxed condition, but then you want to show they're equal to each other. Okay? So we're going to assume a lot of stuff. A equals BQ plus R, and 0 less than or equal to R less than B. And Q and R work. And then same thing for Q2 and R2. A is also equal to B times Q2 plus R2, and 0 is less than or equal to R2 is less than B. And our goal for the uniqueness proof is to say, well, if two things work, they're actually not different. They're the same thing. Which means here that Q2 is equal to Q, and R2 is equal to R. That's the goal. And if you're wondering, well, what about Q1 and R1? Those actually showed up in the existence proof from the previous lesson, and they had a different meaning. Although you are allowed to reuse, just to avoid any chance of confusion if you watch these together, I'll just Q2 and R2. Could have put subscripts over there too, but I didn't want to have too many subscripts. All right. Now, all right, how we do this? So it's an and statement. We have to prove these two things, but the proof templates don't get us all that far as telling us how. So what I'm going to propose is, well, let's look at all this stuff we assumed and see if we can glean information about Q and Q2 and so on from all these assumptions. Okay. So let's... one thing we can do is we can combine these. All right. So we've got these two different expressions for A, BQ plus R, and BQ2 plus R2. They're actually not different, but we don't know that yet. They have different letters in them. All right. And so then the A disappears, and so this is equal to that. And so we can move stuff around. And so I can move the B terms over to the left side and move the R terms over to the right side. Okay. Then I can factor a B out like this. All right. Now, there's different ways of proceeding. One thing I'd like to try is we also want to use this information, right? So let's take a look at, if we know this about R2 and we know this about R, what does that tell us about this difference? Okay, so we know, first of all, by negating this inequality for R, that will flip everything. So minus B is less than minus R is less than or equal to 0 from here. And we also have this guy. And so if we add that inequality, we also know that. We'll just write it directly underneath. Less than or equal, like that. And now by adding inequalities, of course, one of them is strict, one of them is not strict, but when you add them, it will be strict now because one of them was. So adding these, we deduce what? That negative B is less than this sum, this R2 minus R, is less than B. Strict less than on both sides. Okay? All right, fine. But on the other hand, this R2 minus R is also a multiple of B. Notice that Q and Q2 are integers, and so their difference is an integer by closure. And therefore, R2 minus R, which is B times the integer Q minus Q2, is an integer multiple of B. So it's either B or 2B or 3B, or maybe it's negative B or negative 2B, or maybe it's 0 times B, which is also an integer multiple of B. But take a look though. What integer multiple of B could it possibly be equal to? It's less than 1B. It's greater than negative 1B because of this. Well, the only integer multiple of B that's in this range with strict inequalities is 0B. That's the only one. Everything else is outside the range. Certainly 2B would be too big, and so on. So we've got to have R2 minus R is 0B, also known as 0, because of the two conditions combined. That's the only thing that works. Well then, R2 is equal to R, which was one of the two things we wanted to prove. Well, and now once we know that, where's the best place to put that? You could put it here, for instance, or here, any number of places. Let's just put it in here. So once R2 is equal to R, then this guy is 0. B times Q minus Q2 is equal to 0. Where B itself, recall, is not 0. It's not allowed to divide by 0. B was greater than 0. So divide by B, or however you want to say that, we get that Q minus Q2 is 0 from here, and therefore Q is equal to Q2. Which was the other part of the goal. And now we have completed the uniqueness proof. All right. So that's the main thing I wanted to do here, but let me just close with a few additional comments about the generalization. I have not given you the most general division theorem. I've restricted to basically positive stuff. Maybe A could be 0, but no negative A, negative B. All right. Well, it does work, and sometimes you need it for negative integers. So I will state what's true. But for the time reasons, we won't enter into many details of the proof. I'll just say a few words about what you do without actually doing it. All right, but so here's the sort of the full version, at least for what we'll do. The full version allows you to have any integer a, including negative. Well, and almost the same for b. You get negative b, but you still can't divide by 0. So b has to be an integer not equal to 0. Okay. And then, again, I'm using symbols just to make it slightly shorter. There exists a unique, exclamation point, unique pair, QR, a pair of integers. So this might look a little bit funny, but each of these is an integer. Okay, the pair is unique. And what's got to be true? A is equal to bq plus r, as before. And almost this. But remember, now b might be negative, so if you don't want a negative remainder, so you use the absolute value of b as this upper bound. The remainder is greater than or equal to 0, but less than the absolute value of b. And still the quotient q, the remainder r, these exist, they are unique. Okay. So that's a theorem which we may have occasion to use. And just be aware of what I haven't proved. I haven't, if a or b were negative, we haven't specifically addressed that. I'll mention the uniqueness proof is almost the same. We have to throw in a few absolute values and it still works. But existence, because we used induction, you don't immediately get it. I'll just mention the idea, which is that, we have proved it for positive a and b, and you can basically reduce in various cases where either a or b or both is negative. You can reduce to the case of positive a and b proved earlier. And I don't know if it's worth just maybe a little quick little example, which is not a proof, just an example. If a was minus 150 and b was 7, well, earlier we discovered by dividing that 150, positive 150, is what was it, 21 times 7 plus 3. So Q was 21, R was 3. All right, and if you didn't want to have to sort of start from scratch, if we wanted to use what we already knew, you could just multiply both sides of this by minus 1. So minus 150 is minus 21 times 7 minus 3, which is, if we're assuming b is still positive, that's negative 21 times 7 minus 3. Okay. All right, the little trouble is that, okay, I'm not supposed to have a negative remainder. So that doesn't quite work. But the idea is, I could think of minus 3 as minus 7 plus 4, which brings me one more negative copy of 7 that could get absorbed into here. Negative 22 times 7. And then I have a plus 4. So this would be the quotient. This would be the remainder. Let's just make sure, multiplying that, 2 times 7, 14, negative 154. So that does work. Okay. And then you could do various other things, like if you were dividing negative 150 by negative 7, maybe you just move this minus from here to there. And there's different cases that can occur. But essentially, once you've got the positive thing, this is the main trick that you need. You don't always need it, but sometimes you do this to make sure that remainder still is positive in the required range. But we're not going to go through the general proof of that. The other thing we probably won't get to, certainly not right now, we'll come back later if we have time, is, well, what do you use this division for? This is like the first step, this division theorem, in building up to greatest common divisors, for example. And that's a whole series of lessons. And that, in turn, leads us to the fundamental theorem of arithmetic, the uniqueness of prime factorization portion that we didn't prove. One thing I will mention before closing, because I claim, oh, I'm just about to end, and then I say 30 more minutes of stuff. But there are two special cases, or at least one special case of this theorem I want to draw your attention to. In particular, b equals 2. Okay. If b is 2, this is saying that every integer a can be written in this form. The only two remainders you might have are 0 or 1 when b is 2. Here q is in z, for some q in z. And this representation is unique. You can't sort of have, for a single a, that it's got this and also that for some other q. That's unique. Okay. And so this should look a little bit familiar. So this is actually the theorem I've been promising for a long time to prove it, that every integer a is either even or odd, but not both. Here's even. This is the definition of even. Here's odd. And it can't be both, or we violate the uniqueness of the division theorem. Okay. And there's nothing special about 2. I mean, it's sort of the nicest expression if you've got 2, but you can use lots of other b's. Let's say b equals 4, for instance, to get these representations. And it says for instance, each a in the integers has the form either 4q or 4q plus 1 or 4q plus 2 or 4q plus 3, where q is some integer. And exactly one of these is valid for any given a. And you can use this for like cases and proofs. So this leads to a subject called modular arithmetic, where you're sort of worried about basically the remainder when you divide by 4 or whatever. And it's just a nice tool to use in all sorts of proofs, where sometimes you can prove a number theoretic result for all integers by just considering, say, 4 cases based on what the remainder is mod 4, as you would say. Okay, or mod 2, or mod 10, or mod a prime. All right, so I mean, it's a very important theorem, even if it doesn't maybe sound so interesting when you first see it. And maybe we'll come to some of those ramifications in later lessons. But that's it for now. See you later.